Hello and welcome to everyone in Physics Fire. Today we are going to do the next topic of electrostatic potential and capacitance. In this topic, in this class, we are going to see about equipotential surface. This is the topic where we can say 90% chances are there that board will ask you question from this topic specifically. Let's see, by the name itself, if you will see equipotential, right? Equipotential, it means equi means what? Same. So potential means voltage, and then surface, it means such types of surface where potential is going to be what? Same. Let's see, potential is going to be what? Same. If you will see surface at which potential is same everywhere, right? Everywhere is known as what? Equipotential surface. Let's take an example. If you will take an example of what? Sphere. On the surface of the sphere, potential is going to be what? KQ by R. KQ by R. I'm drawing the radius, guys. So we can say from here. Okay. Anyway, so we can say all are what? R. Potential on the surface is what? KQ by R. Everywhere on the surface is going to be what? KQ by R. Right? KQ by R. KQ by R. So potential is same. So we can say such types of surface is known as what? Equipotential surface. Right? Let's see. Suppose if you will take a point charge. For what? Point charge. Guys, for point charge, if you will see, let's take a point is this small, or let's take a dark circle. Right? This is the point charge, and then we want to find what? Equipotential surface for this. So we can say, of course, it is going to be the because radius is same, right? Now let's take again. Radius is again same. Now let's take another color. Everywhere, if you will see on the surface, suppose here is 10 volt, here is 15 volt, here is 20. Oh, we did opposite. We did wrong. Potential will decrease. KQ by R, right? If R will increase, then potential will decrease. 20, 15, and this is going to be what? 10 volt. So for a point charge, equipotential surface is what, guys? Is sphere. Right? For a line charge, if you will take a line charge, let's see, for a line charge, what is going to be the equipotential surface? Positive line charge. Let's take this is a line charge, and this line charge is what? Positive. Right? For this we want to find equipotential surface. So I'll draw it properly so that you can feel what I'm saying. So now if you will draw here, so we can say cylinder. Again, it is what? Cylinder, and then we can consider again so equipotential surface for a line charge is what? Cylinder. For a line charge, is cylinder. Again, for sheet also we can say what? Cylinder. So whatever Gauss law we had done, the same thing. Gaussian surface is going to be what? Equipotential surface. Now if you see properties of equipotential surface, potential difference between any 2 points is 0. Of course, we learned equipotential surface means what? Potential is same. Suppose if this is the surface, if you consider potential here, of course here is also 10, then here also will be what? 10. So net potential is what? 0. So potential difference between any 2 points is 0 inside a equipotential surface. Next point they are saying that what? Work done in a equipotential surface is 0. Let's see how it is. Suppose if you are considering a surface, this is the surface, and you are taking a charge from here to here, distance, let's take delta r, from here to here, you are bringing a charge. If you bring a charge from A to B by applying some force, we can say that potential at A minus of potential at B is equal to E dot dr. Anyway, change in potential is what here? 0. So we can say E dot dr. So E, ultimately everything is going to be work done. Work done is equal to, we can say, we should not write this. Better we'll write what? Work is equal to Q into V. Work is equal to what? Q into V. By mistake I wrote that formula. Q into V. Work, right? So potential is 0, then it is going to be what? 0. So ultimately work is also what? 0. Hope so you got it. So work done in equipotential surface is again what? 0. Two equipotential surface will never intersect. So of course it will not intersect. So let's see. Suppose if one equipotential surface is this, and another equipotential surface we consider is this. Now guys, if you consider two different equipotential surface, let's take potential electric field due to this is in this direction, and for this is in this direction. Now two different electric field, and it is intersecting at a point, which is again not possible. In electric properties of electric field lines, we learned that what two electric field lines will never intersect each other. If it will intersect at the intersection point, we can draw more than one tangent, which is not possible for a vector quantity. So same thing again here, two electric field lines are intersecting. So it contradicts again, right? So it is not possible that two equipotential surface will intersect each other. Let's see the next. Electric field lines are always perpendicular to equipotential surface. Electric field lines are what? Always perpendicular to equipotential surface. Let's see why. Delta V is equal to E dot dr. Okay, electric field lines are always equipotential electric field lines are always perpendicular to what? Equipotential surface. Okay, delta V, if you will see, delta V means what? Change in potential. Same thing, right? Change in potential. Suppose VA and this is what? VB. Distance is what? R. It means VA minus of VB is equal to E dot dr. This thing is what? 0. This thing 0 means E dot dr. Angle should be how much? 90. It means E dr cos 90. Then only this value will come what? Equal to 0. Right? It means E and dr is what? Perpendicular. Finish. Electric field lines are always perpendicular to what? Equipotential surface. It means electric field lines and dr will always be what? Perpendicular. Why? Because this left side we should get what? LHS side we should get 0. So cos should be what? 90 degree. That's it. That's why electric field lines are always perpendicular to equipotential surface. We'll draw 1-2 questions that electric field lines due to a equipotential surface due to a dipole. Guys, if you'll see due to a dipole, if you'll see equipotential due to a, if you'll see electric potential, what is the equipotential surface, right? Equipotential, equipotential due to a dipole, due to a dipole. Then we can say, let's take a positive charge and let's take a negative charge, right? Positive charge and negative charge. Now guys, let's consider like this, right? For a point charge, it is going to be what? Sphere. Right? Again, if you will draw for this, right? Okay. Second thing is what we can say, no, like this, as this is a positive charge and this is a negative charge. We can take more lines. Electric field lines will go like this. So we can say now some of the lines will be like this, right? It will be too big. That's it. And all the lines are what? Perpendicular. Remember this thing also, right? Equipotential surface should be what? Perpendicular. One more example for a uniform electric field. If a uniform electric field is there, then how should be the equipotential surface? How it should be the equipotential surface? Guys, if you see equipotential surface here, is going to be, we know, towards the direction of electric field, equipotential will always decrease. So if this is 20 volt, this should be what? 15 volt. This should be what? 10 volt. Means it should be less than those two, right? That's it. That should be the this question also they asked. So we can say that's all about equipotential surface. Each and every, even for JE also we can say that is what is equipotential surface. Hope so you guys understood. We'll see in the next lecture.